because as Blake pointed out, we've got addition and we got positives and negatives in here from the charges. It's not all going in. Sometimes it's going out, and sometimes it's going in. And so sometimes my potential energy is going to be positive, and sometimes my potential energy is going to be negative, and we'll figure things out as we go. So we define the electric potential energy in a matter similar to orbital gravitational potential energy. We say that electrical potential energy reflects the work that must be done to move a charge Q from a point near the charge big Q out to infinity. So if these guys, let's say big Q and little q, are opposite charges, I am going to have to do work to grab this thing and pull him away, because one is positive, the other is negative. There's an attractive force going on there. So I would have to be doing work to make that happen. If these are the same polarity, when they're both positive or they're both negative, I would have to hold this guy back from being flung away. So there's going to be a set of questions where it's not about, how much is it going to take me to pull these guys apart. One of them is going to be, okay, how hard is it going to be for me to push these things together? And the process is going to be the same. I've got two potential, like if this one's positive and this one's positive, then the work involved is going to be to push these things together because they're trying to repel each other. You cool with that? 3 of you nodded, so I'm just going to assume that is true for the, and Toby nodded, so we're good. So recall the force between two charges is not constant and varies with distance. Fe equals kqqq over r squared, just like Fg was equal to gmm over r squared. Recall as well that with a varying force, the work cannot, important word, be calculated using work equals force times distance. Can't do that because the force is variable with the distance. So there's a whole branch of mathematics dedicated to this, i.e. integral calculus, but we're not going to do that because we've already kind of tried and I hurt some of you mentally. So we're just going to jump straight ahead and say, okay, well, we found before that PE gravitational is equal to negative GMM over R using calculus. And because the forces that we're dealing with have basically identical formulations, then the potential energies are going to have to be basically the same formulas. And so we are going to just go ahead and wave our magic physics wand, which you use when you don't have the mathematical skills required, and say that potential energy is equal to kqqq over r, not negative.
It's because you don't have negative with whatever. Yeah.
It's not negative because now, when dealing with energies, we include, there is no direction with energy. Energy just is a quantity. It's not a vector, it's a scalar. And so because it's not directional, actually, Nathan, that's a really good segue into this. Because it's not directional, we have to include the positives and negatives because we're not dealing with them in any other way. We dealt with them with forces because they were just directions. But now we're not dealing with them as a direction, so we must include them.
Did they not just make like a blanket statement where if they're opposite forces, then the result will be whatever positive? The same force, the result.
See, when you use the language of resultant, the resultant implies vector. These aren't vectors, these are energies. And why use a blanket statement when I can just say, here's the formula, I'll use the positives and negatives and tell me what you get? Like, it's easy. A physicist would say, I could memorize that wordy thing that Blake just said. But why? When we can just say, when I've got direction, positives and negatives give me the direction, don't include it. When I don't have a vector, the positives and negatives aren't dealt with, include them. And it's as simple as that. Still, though, similarly to gravity, at infinity, potential energy is going to equal 0, regardless of the charges involved. Comments, questions, concerns? Going once, twice, 3 times. Flip the page. Let's use this stuff. So, this is 2 scenarios. Well, it's the same situation, but they're giving us both stages of the problem. I want to find the potential energy of a negative 75 microcoulomb charge that is 3 centimeters from a positive 120 microcoulomb charge. We're going to find the work energy equation if it's moved out to infinity, and then we're going to find the work done by the applied force. The questions are going to be posed in a week and a half aren't going to include A and B. They're just going to go straight for this. Find the work done required to move a negative 75 microcoulomb charge 100 infinitely far away from a 120 positive 120 microcoulomb charge. So we're just going to jump straight to this and kind of just chuck it through. To find the work done, whenever they say something like that, especially when you're dealing with orbital gravitation or electric potential or electricity, you're going to have to use the work energy theorem. Energy initial plus whatever work done is going to equal energy final. The only kind of potential energy we have here at the beginning is, dang it, I broke. The only kind of energy we have here is potential. So I've got potential energy initial. There is no kinetic energy because the thing's not moving initially. We have to do work. Oh, we have to assume that work's present because the question literally says, find the work done. Energy at the end is 0. Because it says it starts and ends at rest, and it's moved out to infinity. So that's 0. So I've got an expression here now for potential energy. KQQ over R plus work equals 0. We're going to fill this thing in here, and we are going to use the, what's it called? The signs on the charges. 9 times 10 to the 9. Charge 1 is 120 times 10 to the negative 6. Charge 2 is negative 75 times 10 to the negative 6. The distance between them initially is 0.03. I don't have to square that. Plus work equals 0. If you shove this thing through your calculator, you're going to get a very nice value. The value you should get is 2,700. Negative, sorry. 2,700 plus W equals 0. So just like when we're dealing with gravity, this thing does end up being negative on this side. You have negative potential energy to start. Where gravity puts it in there explicitly, the charge on the objects gives it to us, so that we can add this thing over to the other side and find that the work done must be 2,700 joules, positive work, which makes sense because these things want to stay together, so I'm doing work to pull them apart. I added 2,700 joules to the system. I added work to make that happen. Cool? Page, let's look at another one. Example 2. Find the work required for an external agent to place a 2.5 millicoulomb charge 5 meters from a 1.75 millicoulomb charge, assume the 2.5 millicoulomb charge is initially an infinite distance away. So this is the same setup, except now I've got two positive charges. So it's not going to take work for me to separate them. They're going to do that very well on their own. It's going to take me work to take this positive one and say, no, you're going here. Like shoving a cat and a dog together. Assuming that, dogs and cats hate each other. So, again, I want to find work. Dogs like cats for a little bit. And then a big dog will become very scared of my little cat when she swipes the nose once. So energy initial, what's the energy initial? 0. Why is it 0, Ashton? Because initially it's at infinity and not moving. So this is where we're going to get the 0, plus whatever work we're going to do to make this thing happen. And its final position is going to be where we get this potential energy final. So work equals KQQ over R. Both the charges are positive, so this potential energy is going to remain positive, which again makes sense. I'm doing work. I'm adding work to the system. It's got to be positive to set this thing up. So 9 times 10 to the 9, 2.5 times 10 to the negative 3, 1.75 times 10 to the negative 3 over 5. If you run that, you're going to get 7,875 joules. Again, the point being, these adding the signs on the charges is what's going to dictate whether positive or negative work is done, and it's consistent. It works out. Cool. One more example for you before I lied. We have 2 more examples for you. But see, Nathan asked this question last week. Do we need anything new to find the velocity? Because it doesn't matter if the thing's really big or really small. If I want to find velocity using work and energy, what kind of energy does a moving object have regardless of size? Kinetic. And the expression for kinetic energy will never change. Regardless of size, because the mass is in there already.
Can we do the same sort of thing that we did with circular motion, where we can relate the kinetic energy to 1/2?
Yes. Yes, a similar relationship exists. Because that wasn't circular motion that we were able to do that with. It was orbital energies that we were able to do that with. And the energies are path independent. So, let's look at an alternative scenario. I've got a proton and I've got an electron. Initially, they're starting at rest. We're holding them there, and then we let them go. What's going to happen as soon as I let those things go? They're going to slam together, not apart, Nathan. Because one's positive, one's negative. There's attraction. They're going to slam together. So when you stretch, we bring the hands together. Okay. No, it makes me feel good when you ask the question that literally the next example is going to deal with. Because then at least, I feel good about my resources. So we're told, and you're thinking about where we're going here. Like this is good when my students and I are on the same wavelength. So an electron is originally 2.5 times 10 to the negative 11 meters from a proton. And again, when we give these distances, we're assuming center to center. But again, these things are so small that you don't have to take into account the radius of the individual particles, because I don't actually even think we know what the radius of those individual particles are. It is released and moves towards the proton. That makes sense. Find its speed when it has moved to within 1 times 10 to the negative 11 meters from the proton. These guys are they're coming together. So, we've got starting at rest, KE equals 0. PE is going to have some value. Why is potential energy going to have a value here? Because we're not out at infinity. What kind of energy are we going to have here? kinetic energy and potential energy, because this thing's getting closer and moving faster. So now when I set up my work energy equation, energy initial plus work equals energy final, we're not doing any work. We're just letting things go and things are going to happen. So work is going to be 0 in this case. So initially, we've just got potential energy, and this is going to be equal to the potential energy final plus the kinetic energy finally. And we're concerned about the energy of that electron. So this is going to give me K QQ Ri is equal to K QQ over Rf plus 1/2 mv squared. So at this point, what we could do is insert a whole bunch of values, get a big value for this, a big value for this, could make these things look awful. Or, no, bad Nathan. Because I have this plus term here that includes masses and velocities, I can't do any canceling. But what I can do is I can say, well, I'm going to solve for v, so I can subtract this guy over, and then I can do some factoring out. So we're going to get this, KQQ over our initial minus KQQ over our final. I've seen a few of you do this, and I just want to expose the rest of you to the fact that you can make your math look a lot nicer by not plugging in values so quickly. On this side, I can factor out KQQ, and I'm going to get this. KQQ 1 over Ri minus 1 over Rf equals 1/2 mv squared. I think so too. Oh, no, Blake, I lied to you earlier. There's not going to be a correlation here because the previous one depended on masses and gravitational constants, and this one does not. So no, there won't be an analogous nice little half this equals that relationship here. My apologies. I would be too in his position. So now we can fill this thing in. 9 times 10 to the 9. The charge on a proton is positive 1.6 times 10 to the negative 19. And I include the sign, which I don't have to include because it's positive, but I include the signs because I'm dealing with energy. So my electron is going to be negative 1.6 times 10 to the negative 19. And this is going to equal 1/2. The mass now that I'm going to use is the mass for what object? The electron, because that's the one that's going to have a bunch of velocity. 9.11 times 10 to the negative 31 v squared. Yeah, sorry. I'll put them over here. Dang it. Our initial is 2.5 times 10 to the negative 11 minus our final is 1 over 1 times 10 to the negative 11. So if I run that thing through my calculator, I'm going to get 1 over 2.5 times 10 to the negative 11 minus 1 over 1 times 10 to the negative 11. Close that bracket. 9 times 10 to the 9. Oh, sorry, maybe you want to see what I'm doing here. 9 times 10 to the 9. 1.6 times 10 to the negative 19. Negative 1.6 times 10 to the negative 19. That's the entire left-hand side. Times 2 divided by 9.11 times 10 to the negative 31. I got real big real quick. Square root that number. I got, what is that? 5,508,998 meters per second. Kind of quick. 5.5 times 10 to the 6 meters per second. And if we look at the speed of light's 3 times 10 to the 8. Yeah, we are just to put this into perspective, we are just under 2% the speed of light at this point. Just under 2%. Okay, so to give you guys an understanding of because it's really hard for us to wrap our heads on really big numbers. We just assume as the numbers get larger and larger, we just assume that all big numbers are close to each other. But we ignore, that poster on the wall back there deals with, at the time of the printing of the poster, all known money. Just all the money, how it's allocated. So even just look, if you spend some time to take some time to study that poster, you will see very quickly the difference conceptually between millions and billions. It's not even close. It's not very old. A billion is you're dead. What is your 30? Okay, yeah. The difference between scales of large numbers is huge. Okay? So, yes, this is large. And so we're going to talk later, if we get to it, about the speed of light. And so we say, okay, well, this in our heads, we want to say this is close. One's 10 to the 6, the other's 10 to the 8. That's 100 times difference. This is fast. Nothing compared to the top speed of the universe. Less than just under 1.8% the speed of light. The maximum speed of the no, it's not. There's nothing. Well, okay. When you say theory, you better mean the same thing that I say when I mean theory. It's tested and legit. If anything is, if anything is found to break it, physics will fall apart.
Wait, so they're not.
We'll get there. No, stop. This is special. No, there's no such thing as a tachyon.
I know, but
just stop, Ashton. Stop. Okay. This question here. This example is gross. It looks relatively simple, right? I've got 3 particles there, and I've got a field point x. There's nothing at that point. Field point x is just a point in space. In the diagram below, we're going to find a few things. We're going to find the potential energy of the system, the force and the direction on the upper 1.5 microcoulomb charge, and the electric field and direction at point x. B and C is basically what Zach asked earlier, except instead of, well, the force and the direction is going to be easier, because I've only got 2 to deal with, not 3. The electric field point is going to be harder because I've got 3 to deal with now, not 2. This is the question you asked earlier. I got 2 points and a field point make a triangle. So, yes. This was the electric field one you asked earlier. This one is the force one that you asked earlier. We're going to add to that the P of the system. The potential energy is actually really nice. Okay? Just so we're clear, potential energy, because energy is not a vector, we can just find the potential energy, find the PEs for all combinations of particles, and add. So it's a lot of work, but it's not hard work, as long as you can keep the things together. I would encourage you to organize it, to lay out your work similarly to how I'm going to lay out my work, to guarantee you have the space. Unless you write smaller than me, then do whatever the heck you want. Okay, so here we go. We're going to do A over here. I'm going to introduce a new way of labeling things. Okay, I'm going to call this guy particle 1. We're going to call this guy particle 2. And we're going to call this guy particle 3. Now, I have so much work to do. I'm going to color code my work to make it nicer to look at. Okay, I got particle 1, particle 2, and particle 3. Sorry, 1, 2, and 3. So how I'm going to label this is this. I want to find the potential energy of this combination of 1 and 2 together. And then I'm going to find the potential energy of 1 and 3. I'm going to find the potential energy of 2 and 3, and I'm going to add them all up. You got to make sure you're keeping track of all of the possible combinations. That's what's going to give us grief here. There's only 3 particles, yeah. So 1 and 2, 1 and 3, 2 and 3 gives us all combinations. If there was a 4th particle there, then we'd have to do a lot more work. 4 more, I think. 3 more for sure. Okay, so potential energy, KQ over R. Keeping in mind that when we deal with energies, we've got to include the positives and negatives. So this is going to be 9 times 10 to the 9. I'm just going to use e's for that. In this one, 1 and 2, I've got positive 1.5 micro and positive 1.5 micro. They're the same, so I'm just going to write it like this to save space. 1.5 e negative 6 squared. And their distance is 2 centimeters. Thank you. This guy here, that's 2 root 2 again. But because it's in centimeters, I need to convert it to meters. Now is the decimal is actually a better one to use. So this is going to be 2.8 centimeters. That's root 8, which I'm going to need for this guy here. So I've got 9e9, 9 times 10 to the 9. That's my k. Q of 1 is 1.5 times 10 to the negative 6. Then I'm going to have negative 2.5 times 10 to the negative 6 over 0.028. I did these two, Nathan.
Oh.
That's 1 and 3 with my labeling. Oh, gotcha. Okay. And now I've got 2 and 3. 9e9, 1.5 e negative 6, negative 2.5 e negative 6 over 0.02. If I run all of those things, we are going to find that the potential energy is going to be equal to what? Yes, it's going to be a real number.
Oh, what did I do?
That is the worst.
I just did the bottom one. I'm sorry.
Why did I get such a huge value to this?
Oh, we don't need to put these things in. True.
Okay, this is the value you're looking for. Those of you who are working on it. I would encourage, when I stop to give you guys time to work on it, I would encourage you to do it. Not just sit and wait for your peers to do it. Potential energy you should find is this, unless I screwed up my math. Negative 1.88 joules. Means what? Because if you got these two are going to repel each other, but there's going to be a retraction between these two and these two. So if my potential energy is negative, that means the work. What work am I doing here? Am I holding these together or am I pulling them apart? Potential energy initial would be 0. To set this thing up, my potential energy final would be this. So positive work means I'm doing this. Basically, what I'm doing here is because this is negative, I'm trying to restrict these things. I'm holding them here from slamming together. That's the implication behind that answer. Now we're gonna do this. Black. I'm gonna create some space here. Okay, so that's what I've set up. Over here, we're gonna do electric field. Electric field, actually, you guys should be able to do.
Let's go.
And we're gonna find electric force. So that's C. Here's B. Electric force is going to get done over here. This is B. And because B and C are effectively review, I want you to do them. I'm going to come around. I'll walk around, see what you guys are helping where help is needed. But I want you guys, especially for those of you who didn't have a chance on the weekend to do some practicing here, do these. Find me the electric field at point X and the electric force on charge 1, the upper 1.5 microcoulomb charge. I'm going to go get some water while you're working on that, and then I will come around and see how things are going. Play with it. And feel free to discuss it with the people around you. Don't do it on your own.
Let's start with, what are you gonna start with? I'm gonna start with two. One of these guys.
No, you're pouring it so I'll see the wine. Don't listen to it. It's part of the use that.
I like this. I got 50.6 miles. I like that song. I want to buy it for $50. Wait, so with that, homework, with all the questions that Adams, those are me? I don't buy. Yes, I don't know. I like to. Yeah, I don't know. One of the first that I like to wait. Oh yeah, I do like that. Yeah, I would. Right.
Hey, Tirith, are we working on this? Because it's on one side and you're on the other. Sorry?
I'll get it. You need some. I got a force for class. It's gonna take me a while.
Yeah, but you're ready to see the electric field and the electric force are vector. Yes.
I do this.
Yeah.
Then we go.
Yep.
Awesome. Forces. Yeah. Wait. No, we don't. Force don't.
In forces and electric fields, you do not include the sign because they are vectors. We deal with the signs in the direction. When we are not dealing with vectors, i.e. with energy, we do include the signs. We are going to sum all of that up.
No, wait, but as vector, you can do it in any order you want. Yeah. Like for example, with this field point F, you would have one pulling it down. You would have one pushing it upright and left and right. It's like what we did
Ooh,
already.
wait a second.
North, west, 45 degrees north. I'm doing components.
Oh, that's what I showed you.
We know it's 45.
I just showed you components. I just showed you components. What? Yes. So this one is negative, right? This is positive. It's gonna want to come this way. And this one is positive. It's gonna want to go out. So it's gonna shoot away. And then this one, since it's a triangle, what's gonna happen is it's positive. The components are gonna be this way as well and this way. So you should basically add, subtract the other, these add, subtract the other, so on. So that's gonna work. The nice stuff. I didn't like the first one, so it's not the first one. I just did 0.0 squared. Awesome. Let's go. What are you doing right here? Yeah, I'm making my I like how I wrote electric. No. Then I just did a source. I had my what? You don't know this angle right here. No, no. Oh, no.
What?
Yeah, this thing is degrees for the whole project.
So therefore, this one is 45 minus.
That would have been a rough.
Now with that, we do coastline.
Whatever. You just assume that this is positive.
Yeah.
How are you doing? You just assume that
I
the
am
field
doing
point
it.
are for electric field or what?
No, I'm still doing.
I'm like doing electric field. I'm like,
Oh,
85. I'll give you my
five.
answer isn't yours. It is positive.
It would be 180 minus 45.
Yes, sir. Yeah, Blake. Yeah, Blake.
Field point is. I forgot my sheet.
That's what I looked at that.
Yeah, not exactly.
So that'll be going back. I will pull that.
So e squared equals.
I'm going to break down. So I'm just not quite sure. If I was the governor of these schools, I would make schools start like 10. I'll make it 10 4. If it was a realistic target. I would make how to coordinate with them.
Okay, how we doing, guys?
Very slowly. Progress is slow. Very. Before? Yeah, I agree. Kind of. It's still all that matters. As long as progress is forward, I don't care what speed it is. Yeah. At some point, speed will matter.
Oh, I haven't done the root yet.
No. Hit a bunch of random buttons. No, please stop doing that.
And you got the same one? 86.59. You probably didn't use well. But I it was 50.65. Oh, I thought it was 6.65.
Yeah, add those two together.
I don't know. Which one?
Electric field.
Oh, I haven't started that.
Or even, I don't know, I know the equations are pretty symmetrical.
Yeah, and then you just add them together. They're at vectors. So You need me to come in?
Just look for the like FE, so the KQQ over R squared between 1 and 2 and then 1 and 3.
But I have 3 charges, not 2.
Yeah, but it's still the same on principle. I'm pretty sure.
Wait, you have 3 charges? What do you mean?
Yeah, we have 1.5, 1.5, negative 2.5.
Yeah, you just train about the sky, right?
Well, but the
Yeah, the field point doesn't matter. That's just, there's the flip. It doesn't matter for it's not affecting anything. So just finding the effect of this on this and then the effect of this on this. So this guy's gonna be pushing it, pulling it that way. Oh no, here's the I don't know if you did that.
Oops. I don't like
You know what I'm talking about? Well, you see, this guy, because we didn't include signs, we had to include direction. Like, it's actually negative, it's going to be.
Which one are you doing?
That this isn't going up, it's actually going up. So don't worry about that.
That is absolutely false. Why?
You need to know that.
What?
You need to know that information.
Whoa.
So, yeah, we're seeing. I don't know what I'm doing, I'll be honest. Wait, why'd that go outside? Going down? Oh, that makes it simpler. What's that hat?
So,
Thank you.
I mean,
I think yeah, we definitely did this one's
I got the stuff from this.
This is the same.
Page star, I thought you did coach, it just has to be coach,
But I have 3
45.
Yeah.
So,
The procedure doesn't change. You find the which one are you doing? Electric field or electric force? So the electric field, each one of them is going to provide an electric field in a particular direction, and then you add them up using vectors. So it's going to end up. So now, guys, if you're stuck, I'm going to start. So if you are stuck and want to follow along, great. Otherwise, feel free to continue working on it if you are making substantial forward progress. So Nathan, you asked just now. I have 3. How do I deal? It's the same thing as when we had 2. When we had 2, we found it from one, we found it from the other. We found that one was going this way, one was going this way, and we added them together using vectors. Same thing. Except now I've got 3. The electric field from this guy here is going to go that way. The electric field from this guy here is going to go that way, because he's negative. The electric, that's what it says. The electric field at point X. This guy is positive, so he's going to go up like this. So the easiest way to deal with this is these two are already set up X and Y. Once you find this value, and because this is a square, I know what that angle is right there. What is the angle, Nathan? 45. So you find this guy, break them up into components. It's going to have a rightward component that adds with this one, and an upward component that subtracts from this one. Okay, so I'm going to call this, well, this one's 1, this one's 2, this one's 3, and I should be doing all of this in blue, but I'm not. I'll switch to blue. No, I'll keep it in green. Forget it. I'm over here. So are you cool with calculating the individual fields? Like using this formula, electric field is equal to KQ over R squared. Okay, so then I'm not going to plug in all those values. I'll tell you that the electric field from 1, this guy here, is 33,750,000 newtons per coulomb. Okay, so that's one value you're looking for. Next value you're looking for, E2. The electric field from this guy here, using this distance, 0.028 meters. I'm squaring it because you're using this formula here. The value you're looking for here is 17,219,388 newtons per coulomb. And E3, the value you're looking for there is from this negative 2.2 microcoulomb charge. E3 is 56,250,000 newtons per coulomb. So then I can redraw it down here just to make our lives a little bit easier. I've got this guy going downwards, 56 million. Sorry, 56,250,000. I've got this guy going to the right, 33,750,000. And I've got this guy going this way, 17,219,388. You said earlier, though, and you were correct to say it, that angle there is 45. So I can break him up into components. If I break them up into components, again, that's trig that you can do, so I'm just going to give you the values for that. Upwards here, we've got 12,175,946. And to the right here, I've got 12 million. Ooh, right, it's 45. They should be the same. 175,946. So because these two, Nathan, are acting to the right, they're going to add, giving me one big vector, goes like that. If I add those together, I get 45,925,940. And then I've got this upward one and this downward one. Downward is bigger. So I'm ultimately going to have something that goes like that. 56,250,000 minus 12,175,946 is going to give me 44,074,054. All of these are measured in newtons per coulomb. So my electric field is going to go that way at point X. No, it's electric field is electric field from the charge. So if I'm doing electric field from 1, it's the charge on 1. Electric field from 2 is the charge on 2. Electric field from 3 is the charge on 3. So the value you're looking for here is 63,653,081 newtons per coulomb, and the direction here is 43.8 degrees. Yeah, just use tan. Because this guy's to the right, that guy's down. Those are the values you're looking for the electric field.
Your direction is, we don't do that thing where we don't assume the field point is a positive. We don't do that.
We don't have to do that anymore. We did that to establish directions from positives and negatives.
So then positives are just positives.
Positives are just out from themselves, and negatives are into themselves. So this positive charge is going to be out from itself straight right. This positive charge is going to be out from itself. I labeled these incorrectly. This should have been 2. And this should have been 3. Ashton, say something next time then, man. If you're sitting there smugly seeing my mistakes, don't assume that you're wrong. Sometimes you are, but sometimes I'm wrong. While that might be true, it doesn't exclude the fact that I am wrong too. So 2 is going to go up like that, and 3 is going to go down into itself. Sorry, I labeled this incorrectly. So 1 straight out from itself, 2 straight out from itself, 3 straight into itself. Into, because it's a negative.
Oh, yeah.
Electric fields from negative charges go into themselves. So I get a setup looks like this. And I labeled 1, 2, 3 to reflect charges 1, 2, and 3. Okay? So then electric force. The question says, find the electric force and direction on the upper 1.5 microcoulomb charge. So I'm going to label the forces similar to how I labeled the potential energies. I want to find the force on 1 from 2 using KQQ over R squared. I want to find the force on 1 from 3, but I don't include the positives and negatives in these formulas now. I have to use the positives and negatives to give me the direction. So if this right here is my charge 1, the force from 1 on, or on 1 from 2 is going to go which way? No, which way? The force on 1 from 2, on 1 from 2 is going to go which way? They're both positive. No, I want the charge on this one. Which way is this one going to go? It's going to go up. So I'm going to have an upwards force, F12. Okay, what's going to happen here? I want to know what the force is on 1 from 3. So assume 3 isn't moving. What's 1 going to do? It's going to go down to the right. This is F of 1 and 3. Again, this is lesson 1, I think, 1 or 2. I'm not going to plug the values in. I'm going to let you guys do the value plugging in. What you want to find is that the force between 1 and 2 is 50.625. And the force between 1 and 3 is 43.048. Abigail, those are the values you got? Perfect. Oh, love it. You've got beefcakes. You found them. Okay, so now we can add these things together using vectors, or you can break them up and deal with components. I don't care. This one, though, really nicely lends itself to cosine law. So F12 is going to go that way. Adding to it, F13 going that way. This guy's 50.625. This is 43.048, and that angle there is 45 degrees. It's beautiful. So that guy's going to go that way. Abigail, your value? Resultant, yeah. Love it. And your direction, right, that angle? Yeah, so you found, but you could say that this is 56.5 right of the vertical, or you found the 33.5 above the horizontal. You can quote it either way, I don't care. Those are equivalent angles, but yes, you were absolutely right. Again, this is stuff based on lesson 1 and 2. This is 1 and 2. This is the new stuff up here. But this is what it looks like when we put it all together. You got to fight, and I've been where you are. Fight the feeling that this overwhelming amount of work is going to prevent me from moving forward. Okay? Hands up if you like war movies of any kind. Hands up if you don't necessarily like them, but you've seen at least one. Okay? So it's the classic, you've got barbed wire above you, and there's pig blood and mud on the ground. And this is not that's usually that's what they would do, yeah. Like when they're training for World War II, they got the barbed wire on the top, the pig blood and the intestines are hanging down there. So you're just doing this, and it's awful. But you just gotta keep going. One arm curl at a time. This is what it looks like in its full writing everything out glory. Okay? The overwhelming amount of work is I see before me a field of barbed wire and pig guts. But you got to get through it, and the only way to get through it is to just one step at a time, and you know all of the steps. Electric field from each one. potential energy from each combination, forces for each combination that is necessary, and you just plug. It's really easy to get overwhelmed by the vastness, and you got to do what you can to fight that, because you know the individual pieces. Those of you who have been practicing this stuff and did your homework over the weekend. Okay, if you're not finished, I do want you to finish that. Finish that one. Don't just use my values and say, oh yeah, I could totally do that on my own. Do it on your own or with the people around you, using my values to verify that you're correct. Here's the homework that you've got from this lesson. 1 to 3, 5, and 7.
That's why I stopped talking. That's why I stopped talking.
Just want to make sure that that's consistent with what I've assigned before. That is, you're right. It is. It is. Nothing is going to change unless I look closely here.
I think it's fine.
Yeah, I think it's fine too.
Yeah.
Okay. So I will give you a bunch of time now to play with this stuff, because the only way you're going to get good is to do.